Hello all, welcome back to my YouTube channel. Today we will be discussing about how to generate an object code and an object program for SICXE mission. It is related to the subject System Software and Compilers. The subject code is 18CS61. Today, we will be solving an example program. The question is, generate object code for the following SICXE source program. The given table is the SICXE source program, and also write the object program, that is write header record, text record and end record. The given table is the source statement, which contains labels, opcode, that is object code, and the operands. And also they will be giving some of the mnemonics and their object code with the question to solve the object code. Some of the mnemonics are add, JLT, LT, LDA, LDB and so on, and their respective object codes are given. Now let us generate the location counter value for the following SICXE source program. First, we have to calculate the location counter value for each instruction, that is for this label, that is sum, first, loop and the opcode also for the start, clear, LDA, LDB, base and so on. There are some of the instructions of SICXE mission. These are the types of instructions, that is type 1, type 2, type 3, type 4. These are having some bytes, that is they are the sizes of these instructions, that is type 1 has the size of 1 byte, the type 2 has 2 bytes size, the type 3 has 3 bytes and the type 4 has 4 bytes size. Starting, the address of location counter will be same as the operand value. First, let us take the operand value as 3000. Then for the label, first we'll use the location counter as 3000, and for that location counter we have the value x. Whenever the value is x, then we have to add the type 2 instruction, because the x is the register value. For the register, we have to take the instruction type 2. Therefore, we will add 3000 plus 2 is equals to 3002. The 3002 is the location counter for LDA. Then for LDA, we have the operand as #0. For #0, it is neither a register or nor it have the plus. So we will use the type 3 instruction. So we will add the instruction, we'll add the location counter 3002 plus 3 bytes, that is 3005 bytes. For that 3005 bytes, we will add the operand of #total. For #total also you will get the same. Sorry, not for #total, it is for total. You will get the bytes 4. Sorry, the instruction type 4. Then 3005 plus 4, you will get 3009. You will add the 3009 for location counter. Then you will loop there. The opcode is add and the operand is table, x. For this operand, you will have the instruction type 3. Therefore, we will add 3 bytes. 3009 plus 3, you will get 3003. Sorry, 300C. For this 300C, we will add the operand count, that is 3 bytes. For all this count, loop, total, you will get 333 bytes. So finally you'll get 3015 in the location counter. Then for the reserved word, you have the operand as 1. And for this 1, you'll have the instruction type as 1 itself. Therefore, 3018 plus 3 is equals to 301B. You'll add that 301B in the location count in the next step of the location counter. Then the reserved words. The reserved word have the operand of 2000. The 2000 word reserved word is equals to the 6000 bytes, where it is converted to the hexadecimal value, then you will get 1770 bytes. So by adding 301B and 1770 bytes, you will get 478B. You'll add that 478B to the next step of the location counter. Then again you have the reserved word as 1. Then again 478B plus 3 bytes is equals to 478E. At the end of the location count at the end of the opcode, the location counter value will be 478E. Now we will start with the first instruction, that is clear X. We have to remember that the clear X have the format 2, that is the instruction is 2. Therefore, we have 2 bytes here. The object code will have 8 bytes. The register 1 will have 4 bits and the register 2 will have 4 bits. So total 16 bits. For clear, the object code is B4, and when we solve the B4, we will get the object code as 10110100. For the register 1, the X value is 1. We have to remember it. The value is 0001, and there is no second register, so the value is 0000. Then the total object code we will get as 101101000001 and 0000, that is equals to B410. Now we will go to the next step, that is LDA and #0. This is the format 3, that is type 3 instruction. In this instruction the opcode should be of 6 bits, but here it is 8 bits, so we have to reduce to 6 bits. Starting from left to right, we have to take only 6 bits. Then we have 1 bit of N, that is indirect addressing mode, and 1 bit of I, that is immediate addressing mode, 1 bit of X, that is index addressing mode, 1 bit of B, that is base relative addressing mode, 1 bit, that is program counter relative addressing mode, 1 bit E, and E will be 0 whenever it is a format 3 and E will be 1 whenever it is format 4. And here the 12 bits of displacement when it is format 3 and 20 bits of address when it is format 4. Here LDA have the object code that is 0. Then we will take the opcode as 8 zeros. And the operand given is #0. It is a immediate addressing mode, and we have base address as 0 and program counter address as 0, so we will take the value 0 only. Here we will take the 12 bits of displacement. Then the object code will be the following, like 010000. Now coming to the next step, that is plus LDB #total. For this is the type 4 instruction, which is format 4, which have 4 bytes. The opcode will take the first 6 bits of LDB, which have the object code as 68. Then by seeing this, we will get to know it is also a immediate addressing mode, and because of it because of it is a format 4, we will use 20 bits of address. Then we have to look at the total, a hash total, which has the label of total, and the location counter of this total is 478B. So we'll take the value of 478B here. Then we have to know that we have to use 20 bits of address. Here we have only 16 bits. So we have to add 4 bits of zeros. Then the object code will be 6910478B. Then coming to the next step, this base and total is an assembly directive, so we don't calculate the object code for this. In the next step, you have the add table comma x, which is type 3 instruction, and for the add the object code is 818. Then we have to take the first 6 bits, that is 000110. Then here it is neither an index addressing mode nor an immediate addressing mode. Here the value of n is equals to 1 bit and the I is also 1 bit. So we have to calculate the displacement here. The displacement is equals to the table which have the location counter as 301B minus the next location counter of x, that is 300C. The formula for displacement is target address minus program counter. Then you will get the value 0000000F. This address is in between the range minus 2048 to 2047. That is F value you will get 1111. Then by solving this we will get 1BA00F as object code. Then coming to the next step, that is TIX and count, we have to take the object code 2C and we have to take the first significant 6 bits, that is 001011. Then if we look at the count value, we will get that it is neither indirect addressing mode nor immediate addressing mode. Then we have to find if it has a base relative addressing mode or program counter relative addressing mode. For that we have the formula, that is displacement is equals to target address minus the program counter. We have to take the target address as 3018, which has the location counter 3018 for count, and the next location counter of this register is 300F. Then we will get the value as this. For 9 you will get the value 1001. It is in between minus 2048 to 2047. Therefore the object code we will get as 2F2009. The next step, that is JLT loop. In this JLT have the object code 38 and the first significant bits are 001110. Then here also it is neither indirect addressing mode nor immediate addressing mode for total. Then we have to check whether it is a base relative or program counter relative addressing mode. Then we will put the formula displacement is equals to target address minus program counter. Then we will get the value as minus 9, which is equals to FF7, and it is in between the program counter relative addressing mode. Then the object code is 3B2FF7. The next step is STA total. For this, the STA has the opcode as 0C. Then we will get the most significant bits, that is 000011. And then here it is also neither indirect addressing mode nor immediate addressing mode. Then we have to check whether it is a base relative or program counter relative. First, we have to put the formula displacement is equals to target address minus program counter, which we will get the answer as 1776, but it is not in between the range of minus 2048 to 2047. As we know, the target address for the total is in the location counter of the label table, that is 301B. Sorry, for the total we are seeing. For the total, we have the location counter as 478B to the next to the next location counter of the operand, that is 3015. Then we will get the answer as 1776. If we convert this hexadecimal, then we will not get between the range of minus 2048 to 2047. Then we have to convert it to the base relative addressing mode. Then for that, the formula is displacement is equals to target address minus the base value, that is 478B is the location counter of the label total minus 478B is also a base value, which means here we have the total base address as the same thing 478B. Therefore 478B minus 478B is equals to 0. The base relative address has the value within 0 to 4095. Then we'll get the answer as 0. So it is a base relative addressing mode. Then finally we'll get the object code as 0F4000. Then for the next step, that is R sub, it is a type 3 instruction and the opcode is 4C. Then we will take the first 6 significant bits, and if we see this, it is neither an indirect addressing mode nor an immediate addressing mode. So these values will be 1 1, and then we have to check whether it is a base relative or program counter relative, but there is no operand in this R sub, then these values will be 0. Then finally the object code of this R sub will be 4F and 4 zeros. Then coming to the next step, that is reserve word. For reserve word, we don't calculate the object code. Then coming to the next step, that is end. For end is an assembly directive. We don't calculate the object code, but we can write the starting address, that is 3000, where we have the starting address as 3000 in the location counter. We'll write the same value here. After finding the object code, we will convert this object code into the object program. To convert this, we have 3 records, that is header record, text record and end record. First, we will take the header record. This header record have 19 columns. The first column contains H, that is header record, followed by the 6 columns which contains the program name. The first 3 is sum, the next 3 is left blank. Then the next 6 columns are taken as starting address of the program, that is 3000 we are seeing here. Then the next 4 columns are taken as the length of the program. How to calculate this length of the program? The length of the program is equals to the final length, that is the final or the last instruction location counter minus initial location counter instruction, that is 478E, that is the last instruction counter, where here it is. Then 3000 is the first location counter instruction. Then the value will get as 1780. We have to write this in the header record. Then coming to the text record, the text record contains 69 columns. The first column is contains capital T, which is a text record. Then it is followed by 6 bits, that is program name. It is a starting of the program, which contains the location counter as 3000. We have to write the starting address of the program. Sorry, it is not a program name, it is a starting address of the program. Then followed by the length of the program. I will tell you later how to calculate the length of the program. Then it is followed by the object code of the program, that is from column 10 to column 69. It is the object code of the program. Whatever we have got the value here, this one we have to write here, that is 4B410010000 and so on up to 4F0000. Then from B410, it is of 48 columns. We have to take B4 as one column and 10 as one column. Like that we will get 48 columns. Then it is converted to bytes, that is 48 columns is equals to 24 bytes, where 2 columns is equals to 1 byte. Then we will get as 2 columns is equals to 1 byte, and we have to convert it into decimals. There we will get as 24 decimals. Then we will convert this decimals into hexadecimals, where 24 decimals is equals to 18 hexadecimals. Therefore, this length of the program we will write here. Then coming to the next, that is end record. The end record contains 7 columns. The first column will have capital E, which is representation of end record. Then followed by the 6 columns are the address of the executable instruction. That is the first instruction. So this is all about the program. Thanks for watching.